Hello, this video is about Newton's law of motion, which describes how force affects a motion of an object. So the first law is that when the net force equals 0, then V is constant. So for example, let's say there's an object moving at speed v0, and there's three different forces that is being exerted: F1, F2, and F3. But if the summation of all the forces equal to 0, then velocity would always stay at v0 and it will not change throughout the motion. Second law is that the net force equals to ma. This is the famous equation of F equals ma in Newton's law of motion, and this only holds true when mass is constant. The unit of force is in newtons, and this equals to kilograms times meter per second squared. So for example, let's say a person weighing 70 kilograms is being exerted by a force of 700 newtons. Then the acceleration that is experienced by this person would be the force divided by mass, which would be 700 newtons divided by 70 kilograms, which would be 10 meter per second squared. The third law is that the reaction force is the opposite of the force exerted. What this means is that, let's say there's a tennis racket, and if I hit the tennis ball with the racket, then the force from the racket to the ball is equal to negative of the force that exerted from the ball to the racket. But one might wonder, if the both objects are being exerted by same magnitude of the forces, why would the tennis ball move more than the racket? That is because from the Newton's second law, that the mass of the racket is far greater than the mass of the tennis ball, therefore the acceleration of the tennis ball is greater. Now there are several types of forces, and the first one is weight. Definition of weight is defined by mass times the gravitational acceleration. So for example, a person weighing 70 kilograms has a weight of 70 kilograms times 10 meter per second squared, which equal to 700 newtons. Again, I'm using 10 meters per second squared because the gravitational acceleration g equals to 10 in the F equals ma exam, not 9.8. The second type of force is normal force. This is the force applied by a surface. And it is very important to remember that this is always perpendicular to the surface. So for example, let's say a box that weighs 10 kilograms is sitting on a surface and it is at rest. Because it is at rest and the velocity is not changing, the summation of the force must be 0, which means if I set the vertical direction as y, the vertical forces must equal to 0, therefore the weight of this mass, which is mg, must equal to the normal force. Therefore, the normal force that is applied from the surface to the mass equals to 10 kilograms times 10 meter per second squared, which is 100 newtons. The third type of force is friction. There are two main types of friction, and first one is from a surface. The friction applied from a surface is always perpendicular to the ground, or the surface that is being exerted on. And the definition of such friction force is that force of friction is equal or less than some constant mu times the normal force. And this constant mu is known as coefficient of friction. So for example, let's say there is an inclined plane of angle theta to the horizon, and there is an object at rest. Now, I'm going to set the coordinate system such that the x coordinate is parallel to the surface and y coordinate is perpendicular to the surface. This is a bit unusual in a sense that usually I would set x as like the horizontal, but in the inclined plane, you'll see why I put it as parallel and perpendicular with respect to the surface. Since the object is at rest, the summation of the force must be 0. Therefore, the summation of the force with respect to the y component must be 0 as well. And if I draw the force diagram of this system, there is the weight, mg, and there is normal force perpendicular to the ground, and there is force of friction. Since summation of the force along the y direction is 0, the normal force must equal to mg times cosine theta. Now there's cosine theta because from using geometry, this angle here is theta, therefore the y component of the weight equals to mg times cosine theta from trig identities. Now therefore, using same logic, the force along the x direction must also be 0. Therefore, the force of friction must equal to must equal to mg sine theta, which this is the component of the weight along the x direction, in which this should be equal or less than mu times the normal force, which is mu times mg cos theta. Now solving for mu, I get mu should be equal or greater than tangent of theta. The second type of friction is friction from a fluid, or such as water or air. And the definition of force of friction is force of friction equals to minus kV, where k is a constant. So for example, let's say in a water, a mass is traveling at speed v. Then the force of friction is opposite to the direction of velocity and has a magnitude of kV. Now, for solving the equation of motion of such system, we can use the Newton's law, where F equals ma, therefore negative kV equals m dv dt. For this system, we can use the differential equation, in which I'm going to talk in later videos, but also you can guess the solution, in which I'm going to guess that v of t is going to be initial velocity times e to the omega t. Reason why I'm guessing the velocity as form of exponential is that derivative of velocity is in the form of velocity, in which this looks very familiar to the derivative of exponentials. So if I take a derivative of v of this form, then dv dt equals to omega v, which from this equation equals to negative k over mv. Therefore, omega equals negative k over m, which means v of t equals to v naught times e to the negative k over m times t. Now the last type of force is tension, and this is tension that is pulled by like a string. One of the features of tension is that if tension exceeds some value, let's say T max, then the string breaks. So for example, let's say on a wall, I put a mass on a string. Then there is mass mg applied downward, and there is force of the tension force applied by the string. But if T, which should equal to mg from Newton's first law of motion, is greater than some value of T max, then that means the string will break. So for example, let's say there is mass m, and there is a string that is tied horizontally, and another string that makes an angle theta to the horizon. Drawing the force vectors, there's the weight mg applied downward, T1 that is applied angle theta to the horizon, and T2 that is applied horizontally. If I set the axis such that x is on the horizontal direction and y on the vertical direction, then from Newton's first law of motion, the net force should add up to 0. Therefore, the sum of the force in the y direction must be 0. And therefore, T1 sine theta, which is component of tension T1 along the y direction, should equal to mg. Therefore, T1 equals to mg over sine theta. And similarly, the sum of forces along the x direction must be 0. Therefore, T2 should equal to T1 cosine theta, which is the component along the x direction. Therefore, T2 equals to mg over sine theta times cosine theta, which equals to mg over tangent theta. Oh, sorry about that. So I've prepared some questions from the F equals ma exam on Newton's law of motion. And before watching this video, if you haven't solved these problems, then please pause the video and take your time trying these. So the first problem is from 2016 F equals ma question 3. Now let A naught be the acceleration from the snow, which is force from the snow divided by the mass. Then acceleration from the first 3 meters equal to g, since the textbook is under free fall. But when the textbook is inside the snow, then the acceleration equals to g minus a naught, because the force from the snow is decelerating the textbook. Using the fourth kinematics equation, which equals to d equals to v final squared minus v initial squared over 2a, for the first half of motion, distance 3 equals to final velocity squared over 2a, since initially the textbook was at rest. And therefore, the velocity would equal to square root of 3 times 2 times the gravitational acceleration, which equals the square root of 3 times 2 times 10, which would equal the square root of 60 meter per second. For the second half of motion, distance equals to 1 meter, final velocity equals 0, the square of initial velocity equals 60, and the acceleration equals to g minus a naught. And therefore, solving for a naught, I get g minus a naught as negative 60 over 2, which equals to negative 30 meter per second squared. And since g equals to 10 meter per second squared, a naught equals to 40 meter per second squared. And from Newton's law, the force from the snow equals to mass times the acceleration, which is 5 kilograms times 40 meter per second squared, equal to 200 newtons. And thus E would be the correct answer. The next question is question 10. In this problem, two masses, m1 and m2, is hanging by a string. Drawing the force vector of m1, there's going to be tension T1 that is going to pull the mass upward. And there's going to be the weight of m1 that pulls this mass downward. And the weight of mass 2 is also going to pull this mass downward. So therefore, the net downward force would be m1 plus m2 times g. Force diagram of m2 is similar to m1 in the sense that there's going to be force of tension from this string called T2, and the weight of m2 will exert a force downward. Since these two masses are at static equilibrium, T1 equals to m1g plus m2g, and T2 equals to m2g. But when this string is cut, only T1 would disappear, but T2 is still present. This means that the lower block is going to have 0 acceleration. But for the upper block, the net force equals to m1g plus m2g. Therefore, the acceleration would equal to m1g plus m2g over m1. And plugging in the numerical values, this equal to 2 kilogram times 10 meter per second squared plus 4 kilograms times 10 meter per second squared over 2. And therefore, the acceleration would equal to 30 meter per second squared. Comparing the answer choices to my calculation, D would be the correct answer. The next question is question 20 from the same year. In this question, there is a mass on an inclined plane which is at a static equilibrium. Drawing the force vector, there is the weight of this object at the center of mass, normal force that is exerted perpendicularly, and the force of friction that is opposing the net force. Then if I set the coordinate system such that the parallel side of the incline is x and the vertical side of the inclined plane equals y, the sum of the force in the y direction must equal to 0, which means the normal force equals to mg cosine theta, because the angle of the weight equals to theta from the vertical, which means the vertical component equals to mg cosine theta. Similarly, the force along the x direction must equal to 0, and therefore the force of friction must equal to mg sine theta, which is the component of mg along the parallel side. And force of friction is equal or less than mu times the normal force, and in this case equals to mu times mg cosine theta. Thus, mu times mg cosine theta is equal or greater than mg times sine theta, and solving for mu is equal or greater than tangent theta. And this means at theta max, mu equals to tangent of theta max. Before calculating theta max, it is important to note that force of gravity is exerted at the center of mass, which means for this isosceles triangle, if the force vector of the weight passes this point of contact, then this is when the object is going to start to topple. But because this point is at center of mass, if I extend this force vector and call this half m1 and call this half m2, then the mass of m1 must equal to mass of m2 because this point is at center of mass. Assuming uniform density, this length must equal to this length because the area of this triangle must equal the area of that triangle. And if I call this angle alpha, then tangent of alpha equals to 1/2 because ratio of this side to that side is going to be 1 to 2. Therefore, alpha is going to be arctangent of 1/2, and by plugging into the calculator, this equals to 26.6 degrees. Then if I call this angle beta, then theta equals to 90 minus beta, and since beta equals to 45 degrees minus alpha, this equals to 90 minus 45 minus alpha equals to 45 plus alpha. And therefore, theta max equals to 71.6 degrees. And therefore, plugging in this value of 71.6 degrees into the expression of mu, then mu, which equals a tan theta, is roughly equal to 3. And therefore, on the answer choice, I would pick E. The next question is from 2017 F equals MA, question 13. In this problem, there is a massless rope on a pulley in which at the each end there are masses that are attached. And the masses are big M and big M plus small m respectively. One thing to note in pulley system is that the acceleration of mass big M is going to be the same as the acceleration of the mass big M plus m, because these two masses travel together on a string, which means the distance traveled by these two masses are going to be the same, and therefore the acceleration of those two masses are going to be the same. Drawing the force diagram of the two objects, for big M there is going to be mass big mg applying downward, and there is going to be force of tension applying upward. And for the mass big M plus small m, there is going to be its weight pulling downward and force of tension pulling upward. Now writing the F equals ma expression, for mass m, tension is greater than the weight, and therefore T minus mg equals to m times a. Conversely speaking, for mass big M plus small m, the weight is going to be larger than tension. Therefore, big M plus small mg minus tension is going to be big M plus small m times a. Note that this expression is simply force equals to mass times acceleration. And to cancel out the tension, I'm going to add these two expressions, in which I get m plus small mg minus big mg equals to m plus small ma plus big ma, in which I get small mg equals to 2m plus small m times acceleration. Therefore, acceleration equals to m over 2 big M plus small m times g. Plugging in this expression here to solve for tension, tension equals to big mg plus big ma, which is big M times g plus small m over 2m plus mg, in which this equals to mg times 2m plus small m over 2m plus m. And solving this becomes mg times 2 big M plus 2 small m over 2 big M plus small m. Note that as small m goes up, tension is also going to go up because the denominator is always going to be greater than the numerator. But as small m goes to infinity, this fraction goes to 2 from the limit, and therefore tension would simply become 2 times big mg. And thus, looking at the answer, we can conclude that as small m increases, the tension is also increasing, but this is going to approach a finite constant. And the last question is question 19. Now, in this question, there is a graph of velocity as a function of time. But one thing that we notice is that this graph is not labeled. So we can see that the slope of the first half is 2, and the slope of the second half is 2/3. Of course, we're taking the absolute value of the slopes. But since this isn't labeled, we're going to scale this by some factor a, in which 2a is going to be the net acceleration for the first half of motion, and 2/3 a would be the acceleration of the second half of motion. So the first half of motion is when the block is going on the upward direction. Drawing the force diagram of this mass, there is the weight mg applying downward, the normal force applied perpendicular to the surface, and the force of friction applied on the opposite direction of the velocity, because friction always opposes motion. Since this mass isn't jumping up and down the incline, the net force along the vertical component of this incline must be 0, in which the normal force must equal to mg cosine theta. And using Newton's law along the parallel direction, the net force equals to force of friction plus mg sine theta equals to mu times Fn, which is mg cosine theta plus mg sine theta. And in this case, this equals to mass times acceleration, in which the acceleration equals to 2a. So therefore, this equals to mass times 2a. Canceling out the m, I get mu g cosine theta plus g sine theta equals to 2a. But when this object is moving downward, the force diagram would look similar to the first half of motion, but the force of friction will be pointing upward because this has to oppose velocity. And therefore, the normal force would still be mg cosine theta because there is no net movement along the perpendicular direction of the incline, in which the force of friction would be mu times Fn equals to mg cos theta, and therefore the net force equals to mg sine theta minus mu times mg cos theta. Now in this case, the net force equals to mg sine theta minus the force of friction. And reason that we're subtracting the force of gravity to friction is because the force of gravity is still pulling this object down, which means the force of gravity is stronger than the force of friction. And this should equal to mass times 2/3 a, because from the graph here, the acceleration equals to 2/3 a. Again, canceling out the mass, I get g sine theta minus mu g cosine theta equals to 2/3 a. Writing the equations, my first equation is g sine theta minus mu g cosine theta equals to 2/3 a. This is the equation that we got from the downward motion. And the second equation is mu g cosine theta plus g sine theta equals to 2a. This is the equation that we got from the upward motion. If I multiply this top equation by 3, then I get 3g sine theta minus 3 mu g cos theta equals to 2a. And thus I can subtract this equation to cancel off the acceleration, in which I get 4 mu g cosine theta minus 2g sine theta equal to 0. Canceling off the gravitational acceleration, I get mu equals to 2 sine theta over 4 cosine theta, which is 1/2 tangent theta. And since theta was 30 degrees in this problem, this equals to 1/2 tangent of 30 degrees, in which this equal to 0.29. Therefore, in this question, D would be the correct answer. And the next question is question 1 from 2018A. It is asking me to graph a velocity as a function of time of an object in air. So the motion of this object can be divided into two. So the first one is the upward motion, and the second is the downward motion. Now, since the object is traveling in air, the force of friction takes the form of minus kV. And from this object, there's two forces that is being exerted. Let's say if the ball is moving upward, then the weight of this object is pointing downward, since gravitational acceleration is always pointing downward. But the force of friction is also pointing downward, since this should oppose velocity. Similarly, for the downward motion, when v is pointing down, the weight mg is pointing downward. Meanwhile, the force of friction should point upward. Now, if I write the net force of this object, the summation of the force equals to minus mg. This is minus because the weight is pointing downward, and minus kv, and this should equal to m dv dt. Now, solving for acceleration, I get acceleration equals to negative g minus k over mv. Now, we can solve this quantitatively using differential equations, but we're going to approach this qualitatively. When v is positive, then the magnitude of the acceleration equal to g plus k over mv. Meanwhile, when v is negative, then the acceleration equals g minus k over mv, which is smaller than the acceleration of the positive velocity. This is clear from the force diagram that I drew from here, since when the ball is ascending, the net force is greater, since both of the forces are pointing towards the same direction. Meanwhile, when the ball is moving downward, the two forces are opposing each other, therefore they're canceling each other as well. Now, this means that the change in velocity when velocity is positive must be greater than change in velocity when velocity is negative. So therefore, my guess of velocity versus time is going to look something like this, where the change in velocity is really rapid when the velocity is positive, while the change in velocity is very gradual when the velocity is negative. Looking at the answer choices, it looks like answer choice D fulfills our answer. So the next problem is question number 5. So on this block, there is two mass attached by a string, and it is asking what will happen to this block. Then, drawing the force diagram of these two masses. For M1, the force diagram looks like this. So M1G, the weight of M1 is pointing downwards, and tension force, I'm just going to call it T1, is going to pull this mass upward. Similarly, for M2, there would be M2G pointing downward and T2 pointing upward. But notice how there are no forces along the horizontal direction. Therefore, the summation of the forces along the horizontal direction is 0. Therefore, the velocity along the x direction is 0, which means this does not move horizontally. Looking at the answer choices, it looks E should be the answer. The block does not move. The next question is question 17 from the same year. So the basic situation of this problem is that there is a helicopter, and this is dropping sand, and it is asking what would be like the shape of the sand when this helicopter moved back and forth. And one assumption is that the air friction is 0. So therefore, since air friction is 0, V helicopter should equal to V sand. So when, let's say let's say this is the initial position of the helicopter, and that is the final position of the helicopter. Then, since both the sand and the helicopter are traveling at the same speed, let's say v naught, then therefore, like, the sand that was dropped here should still be right beneath the helicopter at the later position. Which means if this moved back and forth, when this moves forward, then the stream of sand would be perpendicular to the helicopter, and when this switches direction, there's going to be another stream of sand that is parallel to the helicopter's direction. And looking at the answer choice, it looks like D matches to my answer, since this initial stream of sand is from the helicopter moving to the right, and this stream of sand is from helicopter moving to the left. The next question is from 2018B, question 13. So on this problem, there is two block M1, M2 that is stacked on top of each other, and it is asking how much force should be applied to M1 horizontally to make it slide across M2. So the basic situation is that M1 has a mass of 2 kilograms and M2 has a mass of 1 kilogram, and the coefficient of friction equals to 0.2, and the horizontal forces apply horizontally to M1. Then drawing the force diagram of M1, there is the weight M1g, and there's the normal force, and there is the horizontally applied force. I'm just going to call it FA for F applied, and there's going to be a friction force that is applied opposite to this applied force. The summation of the force along the vertical direction should be 0, because intuitively this block won't jump up or down. It's just going to stay at the same vertical level, which means the force along the vertical direction must be 0. Therefore, the normal force equals to M1g, and therefore the force of friction is equal or less than mu times Fn, which is 0.2 times M1g, which is 0.2 times 2 kilograms times 10 meter per second squared. And solving this leads to force with magnitude of 4 newtons. Now, in order for M1 to slide across M2, the acceleration of M1 should be equal or greater than acceleration of M2, because M1's speed should exceed the speed of M2, and in order for M1 to travel at a greater velocity, its acceleration must be greater than those of M2, which means that net force along the mass 1 divided by M1 should be greater than the net force on M2 divided by M2. So the acceleration of M1 equals to the applied force minus the friction force divided by M1, and for M2, only horizontal force is the friction force from M1. Now, the reason why the friction force is applied to the right is that this friction force from M2 to M1 is a reaction force of the force from M1 to M2. Therefore, these two have same magnitude with opposite direction. So therefore, the acceleration of M2 is 4 newtons divided by 1 kilogram, which equals to 4 meter per second squared. And plugging in the value for here, it equals to FA minus 4 newtons divided by 2 kilogram, also equal to 4 meter per second squared. And solving for FA here thus leads to the applied force equal to 12 newtons. And looking back to the answer choice, this is 12 newtons, D. So the next problem is question 15. Now, before I talk about this problem, this question is about weight scale, in which the reading on the weight scale is equal to the normal force that the scale exerts to the object. So in this case, when a person is holding a physics textbook, there is going to be weight of this person and the physics textbook combined, and there is going to be a normal force that the scale is applying, such that both the person and the physics textbook stay at rest. Then the reading on the reading on the weight scale equals to the magnitude of this normal force. So therefore, when this person holds up the physics textbook, then when he or she is holding up the physics textbook, again, this normal force should equal to the normal force initially, since in both situations, the person and the physics textbook are at rest. But in order for this book to not accelerate, but elevate up a level, there should be some sort of positive acceleration and then some negative acceleration to slow this down. What I mean by that is that if I graph velocity versus time, it should look something like this, since the book should go upward and then come back to rest. So from here, velocity is increasing, therefore acceleration is positive, and here velocity is decreasing, therefore acceleration is negative, which means the normal force increases when on the first half of the motion, and then the normal force decreases on the second half of motion. And therefore, if I graph the normal force with respect to time, it is going to stay at some. It is going to be remain constant because initially the person is not moving, and then it is going to increase. That is when the book is accelerating, and then it is going to decrease like this, and then come back to this constant. Now, if I take the area of this change in acceleration, then the change in acceleration, which equals the change in normal force minus the weight divided by the mass, should equals to change in velocity equal to 0. Looking at the answer choices, it seems like answer choice E only fulfills this condition because the positive area here is roughly equal to the negative area here. Therefore, if I add these two area up, the integral of the acceleration is going to be 0. So therefore, I'm going to choose E for this one.